Thank you very much. Okay. This work is about using monads to give a denotational semantics for probabilistic languages. Okay, so let me recap these three keywords here. So a monad on set gives you a denotational semantics for a certain class of effectful operations. It depends on which monad you have, but typically we're thinking random choices or using state. When I talk about the tensor, I'm talking about an operation on monads. So the tensor of two monads is a third monad that gives you semantics for having both sets of operations at once. Okay, it can be quite hard to give an explicit description of the tensored monad. So the problem we were interested in is to try to give an explicit description of the tensor when one of the monads you start with is probability. Okay, and the idea is to start from the fact that probability monads tend to come from semirings. And a semiring is an algebraic structure with an addition and a multiplication. So the main example is the non-negative reals, so from 0 inclusive to infinity exclusive with the usual algebraic operations. Okay. If I fix a semiring R, then I can get two monads out of it. So there's a monad TR, which sends a set X to the set of finitely supported functions from X to R. And these are unnormalized measures on X valued in R. And there's an important submonad where you take all those measures whose total mass is 1. Now, if we take our semiring R to be the non-negative reals, then we get back ordinary probabilities and ordinary finite unnormalized measures. But there's lots of other semirings we might take. And for a probabilistic example, suppose we wanted to infer the bias P of a coin, which we didn't know. We could then work with the semiring of polynomials in P. But note, because our semirings don't have subtraction, we have to include an explicit element which represents 1 minus P. Okay, and then measures valued in this semiring are like distributions that you can generate using a programming language that has access to a coin where you don't know the bias. So T sub R and T sub R1 are quite nice explicit forms for a monad to have. But to get some more examples, we need to generalize just a little bit. So one thing we need is that we need the semiring R to have a possibly non-commutative multiplication, even though in probability, usually the multiplication will be commutative because, say, flipping two coins, you can usually exchange the order of the flips. Right? And another generalization we need is to go from the total mass being 1 to being able to fix a subset S of the semiring, and then looking at those measures whose total mass is in that fixed subset S. And there are some conditions on S that make this well behaved, but we don't need to worry about those. Okay, so many non-probabilistic effects are generalized probability theories in this sense. So for example, global state, where we have, for simplicity, one memory location, we can use a semiring which is generated by the set of all possible reads and possible writes. Now, because reading and writing don't commute with each other, the multiplication in this semiring isn't going to be commutative because we can't swap the orders of two writes operation. We can present the semiring using a short list of equations on top of these generators. So, for example, the equation I've written down says if you write little I to the memory, then write little j. That's the same as just writing little j without the first write. Okay. Now, if you choose the right subset S, then the generalized probability monad that you get is precisely the usual global state monad. Okay. Let's return to the problem I said on the earlier slide. The tensor of two monads corresponds to having both classes of effectful operations, but where the operations from one class commute with all the operations in the other class. So in terms of programming, that says you can reorder lines in a program like we have here, where flipping a coin commutes with, or can be reordered with reading from the state. Okay, so our idea for getting a description of the tensored monad is to use a tensor of semirings, which is a sum of semirings. So a semiring that contains the two starting ones, together with some equation, an equation that says the order of multiplication doesn't matter for things in different semirings. We have a result that says the tensor of two monads of full measures always corresponds to the monad of full measures for the tensored semiring. And we have lots of examples in the generalized case where we get an isomorphism like this. And our main piece of work in progress is to try to find sufficient conditions for which we get this isomorphism. Okay, thank you very much for listening.
Thank you very much, Sean.